Hello, everybody. It's me again, Rich Andre, and today we're going to be talking about an oversimplified version of the Schrodinger's equation. So, what is the Schrodinger's equation? Before we start with the actual equation, okay? Let's first start to define what the Schrodinger equation is. So, the Schrodinger equation, okay? If you could imagine a wave, okay? Could imagine a wave. The wave looks like that, right? So in quantum mechanics, okay, basically just in the wider field of quantum physics, if you have, let's say, an atom, okay, let's just say this is any kind of atom, and you have electrons just moving around it, okay, and let's use hydrogen atom, okay, let's use a hydrogen atom, for example. Okay, one proton, one neutron, and one electron. So the Schrodinger's equation's purpose is basically just to predict what the probabilities are of this electron, okay, of any certain particle that is in the atomic world, okay, that is in an atomic world, or any single particle that is in an atomic world, and it basically just predicts the probabilities, okay, of where that particle is going to be. Is going to be seen. Okay, so it's not really a guarantee. Okay, more or less just a probability. Okay, you're just predicting the probability of a certain particle's location at any given point of time. So let's say you're trying to find out where you could find the electrons. Okay, the electrons that's orbiting this hydrogen atom. You would use the Schrodinger's equation, okay? Because electrons, okay, they're both particles and waves, okay? They're particles and waves. So, now that you know that, okay, let's start with the actual equation. But first, let's go and talk about the psi, okay? The psi sign, okay? So this psi is basically just depicts a wave, okay? So now that we know this, let's write out the full Schrodinger's equation. I believe it's like this: derivative of I think it was something like, yes. Derivative of t equals, I believe it was something like the Hamiltonian, okay? Hamiltonian, we can just, so this is the full Schrodinger's equation. And the Schrodinger's equation basically just says that, basically just tries to predict the wave probability over time, okay, given its potential energy and mass, okay, given its energy and mass. So let me rephrase that. It's more or less just the wave, how the wave changes over time, okay? So we could just try to decipher what the Schrodinger's equation right here entails. This is basically just this just means imaginary units, okay? These are basically just imaginary units, okay? And this h that looks like a t at the same time is the reduced Planck's constant, okay? Constant. So we can just search up Planck's constant right here. We can see, okay, because this is a very big number. I can't really memorize it, so you can see it right here. It's Planck's constant. So obviously you're going to involve that here, but there is a reduced Planck's constant, which is this, okay? Its numerical value is reduced Planck's constant is 105. Yada yada yada. Yeah, okay. So it's basically just that. So given that, okay, now this is a derivative of the wave function over time. So basically, just monitoring the change of the waves. Okay, changes in the wave over time. This is equal to Hamiltonian. Okay, so what is a Hamiltonian? Hamiltonian. This is a Hamiltonian sign. It's basically just I believe it was potential energy and kinetic energy. Yes, I would be correct. That would be the kinetic plus potential energy. Okay, kinetic plus potential energy of the particular particle. Okay, this all just depicts the potential energy. Okay, the kinetic energy of any given particle. Okay, let's say the electron. Okay, let's just say the electron, this hydrogen atom. Okay, so of course this is going to be the sign. Okay, the psi sign, which basically just depicts the waves. So Hamiltonian times psi, I believe. So this is going to be the Schrodinger's equation. Okay, so the Schrodinger's equation, it has a lot of uses. Okay, and not only in the quantum physics world. Okay, this equation has been used in a lot of fields that really have gained as an advancement in technologies like lasers, semiconductors. A lot of the things that we have today, it would be very much attributed to Schrodinger's equation. Okay, so hopefully, right, this simplification helps for you to understand. Okay, sort of an overview for the Schrodinger's equation is, and what it entails, and what it describes. Okay, so that's basically it for Schrodinger's equation. Okay, I could have went deeper with it, but I think this explanation really just suffices if you're just trying to have a little bit of a knowledge on the Schrodinger's equation. Because if you try to deep dive into it, it'll probably take longer than the whole duration of this video, like 3 times it or 4 times. Okay, so that's basically it. This is Schrodinger's equation. If you guys learned anything, please give me a thumbs up. Subscribe. If you didn't like the video, you can give me honest feedback in the comment section, and I'll be sure to read. So tune in on another video, guys. Thank you for watching. Thank you for listening.